Hello everyone. So as we have learned about stoichiometry, now we will learn about the basic reactors where the reaction takes place and where we will use the applications of stoichiometry in further studies. So before going to the reactors, we have to know the basic balance of any system. Suppose this is the system of our interest and this is inlet and this is outlet. Now to do basic balance of anything, it will be inlet plus generation, which is equals to accumulation plus outlet. Now this is the basic balance of any quantity which we will be balancing. This may be mass balance, material balance, momentum balance, energy balance, any balance. So the accumulation term will have certain time derivative dou dot t or ddt. If it is fixed in space, it depends. So this is any basic balance of any system. Now, this is with this knowledge or with this concept, we will go further and we will study mm, three broad categories of reactors. One is batch, another is mixed flow. It is also called CSTR, and the last one is plug flow. Note that these three reactors are ideal reactors. Ideal reactors, it means in reality or in industry, there is no such kind of batch, no reactor which will be perfectly batch or perfectly mixed or perfectly plug flow reactor. For dealing with non-idealities, there are certain concepts like residence time distribution or RTD or some models are there. Those will be those we will see in later. Those are non-ideal case which includes diffusion and some other things. But in most cases, by introducing some external mechanical things like agitators or something like this, 90% we can attain ideal reactors. We can 90% go near up to ideal reactors. Now the first one is batch reactor. Now the batch reactors. Batch reactors, as name suggests, are processed in batch where a closed vessel is there. This top portion of closed vessel, it may or may not be fixed. If it's a gas phase reaction, then it might not be fixed. For phase reaction, for controlling pressure, this thing will change its position, or some something like that will be there. In liquid phase reaction, it will be closed. So it depends. Now, for doing material balance in batch reactors, as in batch reactors, there is no inlet, only generation is there, RAV equals accumulation is there because it's the batch inside the accumulation and there is no outgoing. Give it time. This one is T. So this is the performance equation of batch reactors. Na is the moles, volume is the V, and Ra is rate of generation of species A. If species A is reacting, Ra is if it is reacting, then Ra is negative, and if it's producing, then Ra is positive. Now, if Ra is A species is reacting, then Ra is negative, and it is mostly written as minus of K times concentration of A, where K depends on temperature, pressure, or it may also depend on some other species if impurities are there. The K is function of temperature, pressure, and Ca is concentration. Actually, it should be function of Ca. It should be minus K into function of Ca. Some function of C and K is function of temperature pressure. Now, in batch reactors, this Ca is concentration and there will be an agitator. This Ca is the concentration of each point in the batch reactor. This is a batch reactor. Ca is uniform across the the batch reactor. Inside the corner here also Ca will be same. This corner also Ca will be same. Inside this also in middle part also Ca will be same. So in that means the Ca is homogeneous across the batch reactor. And in real industrial application, there is a agitator provided which rotates very fast and mixes everything. So this this mixture will be almost 90% homogeneous. So in industry, this gives a rough ballpark that if the reactor is 90% ideal, then we can use the assumption of batch reactor. Now for suppose now if the volume is fixed, if the entire thing is filled with liquid or gas, if the volume is fixed, this volume is the volume of the reacting species. It may be it may be equal to the reactor volume or may not. It depends. Or the reactor volume may itself change if the supporting overhead changes its position. But suppose if the volume is constant, if is constant, constant, sorry, CO V is constant, then this expression will be Ra is equals to d Na by V by dt. Now, as I have said that in batch reactor every point is homogeneous. So this Na is total moles inside the total moles of A inside batch system. This Na by V, this can be written as dCA by dt. This is the concentration of A. And for example, this a function, this is a first order reaction, then this can be again written as wait, for first order reaction, Ra is equals to minus KCA. Again, note that Ca is homogeneous in the inside the batch reactor. So for batch reactor, we will get dCA by dt is equal to minus KCA, which easily can be integrated and expression of this form can be written. This is time. So this gives a rough idea of batch reactor. Now there is another type of reactor which is called semi-batch reactor. Semi-batch reactor. This name suggests that this is a semi-batch because it's a batch reactor where nothing product is withdrawn but a stream is supplied. This is this is agitator. A stream is supplied. The volume is like this. This is some volume P, volume of the fluid. Suppose B is added, and in this fluid A and a catalyst is there. Catalyst is there. A species A and catalyst is there. Whenever B is added, the reaction happens. This is maintained by certain temperature. So these external things are taken care of in this understanding that external temperature pressures are somehow kept. How it is kept, we will see this in later lectures. Now suppose B is added with a volumetric flow rate of Q with a concentration of Cb naught. Now this is a semi-batch reactor. Now to do the balance of semi-batch reactor, we will do the balance for each. Now to do the balance in the semi-batch reactor, we will take the balance of A species. Now there is no inlet of A plus generation RAV is equals to dNA dt plus 0. There is no withdrawal from it. This is A balance. And for doing the B balance, Q CB naught, this is the inlet term plus RBV is equals to dNB by dt plus 0. Now, see one thing, this volume, in this case, the volume will be changing like this. V is equals to V naught plus Q into T. This volume change, this is assumed by if the density is constant. Assume density does not change. Now, these species are concentration of certain thing. Density will not change in most cases. If it changes, then this volume will not change like this. Some density terms will be there. But in this case, see that the volume will be changing. So here you cannot just directly divide or take or write Na. You can write Na as Ca into V. This concentration or Nb is equals to Cb into V because it is homogeneous at every point. This is the assumption of semi-batch reactor. But these are in derivative term. So if you write the balance of A, if you why we are writing in terms of concentration? Because the rate expressions are mostly expressed in terms of concentration. So for balance of A species, you will write RAV is equals to dCA into V by dt, and again you have to differentiate the V also. CA into dV by dt. dV by dt is the rate of increment dV by dt. Now dV by dt can be done from here. If the density is not changing, dV by dt will be the addition volumetric flow rate V dCA by dt plus Ca into Q, and Ra can be expressed in terms of concentration. So this is how, and this V will be some function of T. So you will get a differential equation, and also so same case as B. So for semi-batch reactor, you have to be very careful because the volume will not be changing. In semi-batch reactor, the mostly semi-batch reactors are used in liquid phase case. Batch gas phases are also used, but with certain exception. We will see that in later examples. In liquid cases, semi-batch reactors are mostly used because volume changes because you are adding external stream flow. So here volume will not be taken constant, so you have to differentiate it. And this concentration is homogeneous across the reactor. So this is semi-batch reactor. Now, as we have seen in semi-batch reactor, there is another type of reactor which is extension of semi-batch reactor. You can say that, but it is not, which is called mixed flow reactor or CSTR. It is also called MFR or CSTR, whatever you call. In this case, this is also kind of a batch reactor, but a different. Here also an agitator is there, inlet stream is there, but here also an exit stream is also there. And the assumption here is that the exit stream concentration and whatever uh, inside the CSTR, those will be equal. Mean if here if concentration is Ca exit, here also it will be Ca exit. If the temperature is T exit, here also T will be T exit. So this is the assumption of CSTR, that the exit and whatever, this is not assumption, this is mostly in any reactor. Whatever the exit case, exit stream condition will be just equal to the immediate inlet of the reactor, immediate pipe inlet. Immediate, what I mean by immediate pipe inlet, suppose this is the exit stream pipe. This is the immediate, this point. This is the exit pipe. This is the immediate inlet. This point is immediate inlet, and these conditions will prevail at the outlet. So, and this, as this is a homogeneous, so this condition will be present entirely in the system. So it is obvious that exit concentration or exit conditions of temperature pressure will be equal to whatever inside the CSTR. Now to the CSTR balancing. In in most cases, the steady state balance is there. That means, what do we mean by steady state? There is no accumulation term present in the system. So inlet stream flow, suppose it is Fa naught, this is molar flow rate of A plus generation Ra. I am writing is V. This is the volume of the CSTR, because CSTR is fixed, entirely filled with volume. If it is not filled with, if entirely filled with volume, then the V is the volume of the reaction phase wherever the reaction is taking. It is understood, and this is equals to if A exit. Now, if A exit, now this can be again written as in terms of conversion if A naught 1 minus XA. This can be simplified as minus RA exit V is equals to if A naught, suppose this is exit, if A naught XA exit, then it can be written as V by if A naught is equals to XAE by minus RAE. If you do not want to write in terms of conversion, then this can be again written as in terms of concentration. QCA naught is the inlet plus RAEV is equals to QCA exit. This can be again written as QCA naught minus CAE is equals to minus RAEV. Now RA reaction A E will be reaction rate A exit will be something minus K function of C A exit. So you can write anything. You can write rate expression in terms of conversion. You can write rate expression in terms of concentration. It is your choice. Whatever whichever is preferred, you can write. So both. So this can be again written as V by Q is equals to V by Q is equals to CA naught minus CAE by minus RAE. So whatever performance expression you may use, these are all equal. For first order, it is easy to derive what will be the exit concentration. So this is mixed flow reactor example. And another case is there. It is called another reactor case. It is called PFR or plug flow reactor. Now in plug flow reactor, the species, suppose this is a pipe, plug flow reactor are tubular reactors. Plug flow reactor is a assumption of a tubular reactor where the streams move in a plug, where the velocity profile will be like this. It will move like a plug. This is an assumption. In many real industrial cases, this might not be case. You have to use certain mathematical approximation like Airy-Stellar diffusion, which will come later, or RTD, or any kind of thing. But if the fluid is mostly viscoelastic or non-linear, then profile will be curved, but it will be almost straight. So this assumption will give correct answer or correct results up to 90% correct result with a certain small error margin like 5%. So studying plug flow reactors is very important because the errors in the plug flow reactor will be very less, like 1% or 2% from the actual perfect value. So studying this is very important. Now for plug flow reactor, to get the performance or the material balance, suppose this is the reactor and suppose this is the X distance along the reactor and this is the corresponding volume which is equals to certain area cross section into X. Now at this volume, suppose we have certain dV. This is volume V. This is volume V plus dV. Now if we magnify that dV volume, inlet is FA and outlet is FA plus BFA and generation is RA into dV. If now FA in this case will be function of volume, which is again function of length of the reactor. So this FA is function of volume and which is again a function of length of the reactor. So to do material balance or species balance of A species FA plus RADV, this is generation term RADV is equals to FA plus BFA, which is outlet term, and there is no accumulation term. As I have said, this except from batch reactor, other two reactor like mixed flow and plug flow, these are assumed to be operating in steady state, so there is no local accumulation. Local means there is at fixed location. Suppose location X, there will be no accumulation. At location X, there will be no accumulation. So this is it. So if I simplify it, we will get dFA by dV is equal to Ra. Now, if I want to write this expression in terms of concentration, I can write Fa as Q dCA by dV. Remember this Fa is Q into Ca. If it is a gas phase reaction and the volumetric flow rate is changing along the x direction, then whatever I have written is wrong. You have to differentiate Q also, but for constant density, this is okay. Q into D or liquid phase or simply liquid phase. Q dCA dV is equals to Ra, and you can write dV by Q is equals to dCA by Ra, and integrate this expression to get volume by Q dCA by Ra from Ca naught to Ca. If we get this expression, we will get the value. Or much safer option is write in terms of conversion. FA will can be written as FA naught 1 minus conversion of A. Now as FA is a function of volume, which is in terms, which in again in turn function of position, XA will also be a function of position. So by putting this expression in dFA by dV is equals to RA, we get FA naught dXA by dV is equals to RA. Now this can be simplified as dV by FA naught is equals to dXA by minus RA. Volume plug flow by FA naught is equals to 0 to XA exit concentration dXA by minus RA. Now let us compare uh, this expression, the mixed flow expression and plug flow expression. For mixed flow, for mixed flow, HA naught is equal to XAE by minus RAE. Now these two expressions can be very much in another one thing to say in industry, continuous reactor streams are used because in industry no you have no time to process batch reactors because you in batch reactor you have to load the material, let it react and again unload the material. It is long time. So in most industrial reactors are flow based reactors. For understanding the flow based reactors and what combination of reactors will be used is very important. Now, if we carefully see this expression, if we plot graph between conversion XA and minus 1 by RA, we will get certain kind of graph. Now, suppose this is the exit concentration XAE. Now, to get the expression of RHS expression for CSTR, suppose in case first we take CSTR. CSTR, this is XAE and this is minus 1 by RAE that is evaluated at exit concentration. So this is the value. So this value is 1 by minus RAE. So this expression, if we write the CSTR expression 1 by minus RAE into XAE minus 0. So this is the y coordinate and this is the x coordinate product. So this is the V by FA naught. This area is the V by FA naught. Vm by FA naught. Vm by FA naught is the area, area. This is A1. Suppose this is area A1, A1. Now same, for same curve, XA 1 by minus RA, for same curve. My hand is not able to draw the same curve, but for same curve, this is the exit concentration. If we take this integral expression, This integral expression 0 to x a t b x a by minus r a. This is the integral expression, which means this is the area under this curve. This is A2. So V plug flow by Fa naught. Vp means volume in plug flow is area under integral, which is A2. Now for this curve, A2 is less than A1. Hence volume required in plug flow is volume less than mixed flow. For this type of reaction curve or whatever the reaction happening in, we are aiming to achieve, the plug flow will give the least volume and hence least cost. So this is very important understanding. And suppose another case. Now the rate expression is like this. Now the rate expression curve is like this. And this is the XAE inlet. Sorry, AE means outlet. XA conversion. Now if we use plug flow, the area will be this one. This point is 1 by minus RAE. So this is the area. So V3 is, suppose this is A1 dash. This V mix flow by Fa naught is equal to A1 dash. And for the same curve, minus this is minus RA XA, and this is exit. This entire will be the plug flow area. Suppose this is area 2 prime. So V plug flow by Fa naught is equals to area 2 prime. Now in this case, area 1 prime is less than area 2 prime. Hence V mix flow is less than V plug flow. So for this case, mixed flow reactor is much useful or will give least cost. Let us take another case. Let us take another case. Suppose the reaction is such that it is like this, and you want to take conversion up to this XAE, and this is 1 by minus RA. Now, in this case, to get the minimum volume of the reactors, total volume of the reactor, if you use a single reactor, if you use mixed flow, then this area, this entire, this rectangular area will be the mixed flow, which will be huge. And if you use plug flow, then this area, which seems to be less than mixed flow, but still large. But if we use two reactors, suppose this is x1 point, and up to this we use mixed flow reactor, and after this we use plug flow reactor. This is CSTR and this is PFR. Then the total volume will be minimum. Then the total volume of CSTR and PFR, or the total material cost, will be minimum, and hence it is much more useful. So we have to design such that the CSTR exit concentration will be x1, and after that it will be PFR. This will give the minimum volume. So the expression V plug flow by Fa naught is equals to 0 to XAE dxa by minus Ra and V mix flow reactor by Fa naught is equals to XAE divided by minus Ra E, which is evaluated at exit. These understanding of this expression will tell how the reactors should be arranged to get the best or least cost of the volume or expenditure of the reactor. Now let us take a generic case, a general nth order reaction Ra is equals to minus Kca for variable density system. Ca is equals to Fa by Q, which is Fa naught 1 minus Xa. If the temperatures are constant, then Q can be written as Q naught 1 plus epsilon A Xa, which is equal to Ca naught 1 minus Xa 1 plus epsilon A Xa. Remember, this expression is only true if temperature and pressure constant, or if T and P are constant. Ca to the power n, nth order reaction minus K Ca naught to the power n 1 minus Xa divided by 1 plus epsilon A Xa whole to the power n. This is the general rate expression for nth order reaction. Now if you plot this, if you plot minus 1 by Ra, which will be equals to 1 by Kca naught to the power n 1 plus epsilon A Xa divided by 1 minus Xa whole to the power n. If we plot this in y-axis, suppose n greater than 0, sorry, n greater than 1 minus 1 by Ra. If we plot this, then we will, for a constant epsilon value, we will get something like this, a sharp increase at this is 1. Remember that Xa range is from 0 to 1, and and for suppose exit conversion in XAE, then for this case, the plug flow will give the least volume for n greater than 1. This is XA conversion. And for n less than 0, for n less than 0, and n is negative, the curve will be like this. This is 1, and suppose this is XAE, exit conversion which is desired. Then the plug flow, sorry, mixed flow. This is PFR will give least volume, and this is MFR or CSTR will give the least volume. And for n is equals to 0, for n is equals to 0, both will give the same volume. Hence, n is equal to 0 is either you use PFR or CSTR, both will give the same volume. Yeah. This you can see by both performance expression. You can integrate and see both will give the same expression. So understanding this is very useful. Now there is another thing which is called fractional yield. Fractional yield. Fractional yield, which is also very useful now, useful in flow based reactors. There is another distinction I forgot to mention. One is batch reactor and flow-based reactor. Inside flow-based reactor, PFR, CSTR comes. So fractional yield is used in both the cases, flow-based or batch. Now, yield has different meaning in different contexts. It is defined upon the problem, but the definition which I am stating now is based on Levenspiel's textbook fractional yield. And fractional yield is defined as rate rate or for of formation of rate of formation formation of desired product divided by rate of consumption of reactant. Now suppose desired product is P. Suppose it is in CSTR, sorry, in PFR. As I have told that in PFR, each section or molar flow rate is is dependent on the axial length of the PFR. So fractional yield, which is a function of volume or function of axial position, it can be written as suppose desired product is P, dFB by minus dFA. Means at that position, at that location, this is instantaneous. This definition is instantaneous fractional yield. That is at that position or at that location. This is the fractional instantaneous fractional yield. Now this can be again represented as Rp dV divided by minus Ra dV, which is Rp. This is Rp by minus Ra. So again at that position, rate of formation of P divided by rate of consumption of A, which is the actual definition of the yield is defined. And for mixed flow reactor, for mixed flow reactors, for the MFR, this yield is defined at the exits. This yield, which will be equals to, suppose P exit divided by, this is the desired product concentration at exit. I am assuming this is a liquid phase reaction. Concentration and moles are same. Means we can divide it by MFR volume. So it will be either Cp. This if the volume is changing, then this Cp will be replaced by n moles for rate of moles or simply Fp at exit. Fp at exit, but volumetric flow rate it is a constant density system, so it is getting cancelled out. Cp exit divided by Ca naught minus Cae. This is the consumption. This is the fractional yield, and this is equals to Rp exit divided by minus Ra exit. Now, we do not need to remember fractional yield concept. You can easily get it. Suppose in case of PFR, suppose in case of PFR, dFP by dV is Rp, we know, and dFA by dV is Ra, also we know. Then fractional yield directly is dFP by dV, sorry, dFA. You can directly get the expression in terms of desired variable. In case of CSTR, sorry, In case of CSTR, this is PFR. In case of CSTR, suppose FA naught plus RA exit V is equals to FA exit and this product. So suppose desired product is FP. There is no inlet of FP or PEV is equals to FPE. Then this expression, above expression can be written as minus RAEV is equals to FA naught minus FAE, and the product case it is already RPEV is equals to FPE. Now if you divide the expression FPE divided by FA naught minus FAE, this is fractional yield which is equals to RTE divided by minus RAE. So phi, which is rate of generation of product divided by consumption of A, phi is evaluated at exit. So this can be written as phi exit. So this is also can be written as phi exit. In instantaneous, phi is actually rate of product formation of product divided by consumption of A. But you can directly for CSTR directly at exit condition you can evaluate it. And as I have said that if P if the density is constant, then Q can be this can be expression as Q CPE divided by Q PA naught minus PAE is equals to RPE divided minus RAE, which is equals to CPE divided by PA naught minus CAE is equals to RTE by minus RAE divided is equals to phi at exit. Now, in many cases, as I have said, fractional yield is, as from the definition of fractional yield, rate of formation of desired product by rate of consumption of reactant. This is basically RT divided by minus RA rate. In many cases, experimental data are used. If the reaction RP and RA expressions are very complicated, phi phi is used. Phi graphically it is known. Now, if the phi value is function of concentration, it is given concentration of A, which is the reacting species. Then, from definition of phi, dFP by dFA is equal to phi, which is a function of Ca. If the system is of constant density or liquid phase reaction, then we can write dCP by minus dCA equals to phi into Ca. If epsilon A is equal to 0, that is constant density or liquid phase. Liquid phase reaction. Liquid phase reaction. Liquid phase reaction. Then the Cp can be easily integrated between phi Ca into dCA Ca naught Ca exit, which is equals to phi Ca into dCA Ca exit into Ca naught. Ca exit will always be less than Ca naught because A is reacting species. And similarly for mixed, this is for PFR. Similarly for MFR or CSTR, CSTR, the expression can be written as CPE divided by CA naught minus CAE phi at exit. CPE is equal to phi at exit CA naught minus CAE. Now this is again graphical based thing. If this is the concentration Ca and if this is the phi, then if it is like this is CAE and this is CA naught. Now to achieve the highest product for if suppose if you use MFR, then from this expression phi A exit, this is the exit, phi exit. If you use MFR, then this is the value of product form, which is less. But for this same case, if you use plug flow reactor, this is CAE, this is CA naught. But if you use same plug flow reactor, the product form is more. So for the case one, suppose this is case one, CA, sorry, C product mix flow is less than C product at plug flow. Again, if the case two, if the curve is like this, phi is CA, this is exit concentration, and this is inlet concentration. So this will be phi at exit. So this entire area will give the product. So in this case, CP mixed flow is greater than CP plug flow. For plug flow, if we see the area in the plug flow will be this is CA, this is CA naught, this is CAE. So area in case of plug flow, this will be the area. This is MFR, this is PFR, this is MFR, this is PFR. So the product formed is also very much important if fractional yield is known. Fractional yield or how it will vary with function concentration of A, it is very important. So this gives case 1, case 2 gives idea how to use fractional yield. Fractional yield, this one is the rectangle for product of exit concentration at exit condition and change in the CA naught minus CAE.